Good afternoon, everyone. Welcome to this week's Kent seminar. Today we have Professor Zhibin Chen with us. Dr. Zhibin Chen is an assistant professor at New York University, Shanghai, and a global network assistant professor at New York University. Prior to this appointment, he was a research fellow at the University of Michigan, Ann Arbor. Dr. Chen received his PhD in transportation engineering from the University of Florida in 2017. His research interests include electric vehicle behavior, policy and charging infrastructure, as well as the design of innovative and sustainable transportation systems. Everyone, please join me in giving a warm welcome to Professor Zhibin Chen.
Thank you for the introduction, and also it's a great pleasure for me to be here to share the one of our work on the value of orderly electric vehicle charging in carbon emission reduction. So it's a joint work with my PhD student, Zhi and professors Haolong, Cheng He, and Hui. So I'm gonna start my talk. So I prepared the slides. I mean, it's such that just for kind of like the interaction, okay? But I was told that I should finish my talk first, and then we can have Q&A section, okay? So this figure plots the surface air temperature anomaly in 2024. Okay, and it has been recorded that last year is the first year to exceed 1.5 degrees Celsius above pre-industrial levels. So if some of you guys have heard about the Paris Agreement, you will notice that 1.5 degrees Celsius is an important Paris Agreement goal. Okay, actually so we expect that we can control it. Unfortunately, so this is the fact. Okay, we already achieved 1.5 degrees Celsius. This is not written, right? It suggests that we need to adopt a more proactive action to control the temperature increment. So you'll notice that the greenhouse gas emission is one of the major factors to the temperature increment. Okay. And it was reported that the transport sector was responsible for 25% of the global greenhouse gas emissions since 2010. Then we will think about that. Hey, what if we can electrify the transport sector? Then can we significantly reduce the greenhouse gas emission? Yeah, the good news is that electric vehicles may reduce the greenhouse gas emission contributed by the transport sector by 50 to 60% in the Europe, and by approximately 40% globally. Okay. As a result, there are many countries and cities actually propose agenda to phase out gasoline vehicles and to adopt the electric vehicles. Okay. However, the amount of carbon emission reduction yielded by electric vehicles heavily depends on their charging schedules. For example, if the electric vehicle, if the electricity supporting the electric vehicle comes from the green energy source, for example, the wind power, solar power, okay, the carbon dioxide emission is only 5 to 15 grams per kilowatt hour. But if such an electricity comes from a polluted source, such as coal, okay, then unfortunately it could be as high as 1 kilogram, 1,000 grams carbon dioxide per kilowatt hour. Okay, so then if the government would like to reduce the greenhouse gas emission, then by adopting the more electric vehicles, then the question is that they need to investigate what's the maximum potential, okay, of carbon dioxide emission reduction brought by the electric vehicles. Okay. So this is another figure to show the hourly electricity generation by source. As we can see, okay, as the time varies, actually the portion of the electricity generated by different sources may vary significantly. Okay. So I would like to use this figure to highlight that charging schedule is really important. Okay. Then the question is that what's the maximum amount of carbon emission that can be reduced by electric vehicles when they behave properly? Okay, where we define it as the orderly charging behaviors. So answering this question is equivalent to answering the question that what's the potential of carbon emission reduction brought by the electric vehicles. Okay. If it turns out that such potential is pretty mild or pretty small, then we cannot count on the electric vehicles adoption to reduce the greenhouse gas emission, right? So several scholars have conducted research to answer this question. For example, Dixon, actually in 2020, they calculate that, hey, 30% of the carbon emission can be reduced through scheduled charging. Okay, this is good. Okay. However, Uber in 2021 mentioned that, hey, only 1 to 10% energy saving can be yielded by the marginal emission factor optimization. Anyway, it's related to the charging schedule. Okay. However, most of these studies were conducted based on simple data survey, okay, or simulated profiles instead of the real electric vehicle travel behavior. So the problem is that by doing that, the estimation may not be accurate. Okay, for example, the survey in general is kind of like biased, okay, subjective, okay, and also because if we only consider the survey or the simulated profile, actually we ignore the impact of charging behaviors on travelers' trip trends. Okay, what does it mean? It means that, hey, for example, I in the survey I highlight that, okay, today on every day, okay, I need to charge 10 kilowatt hour, okay, from 6 to 8 p.m. Just for example. But the problem is that what if tomorrow I'm gonna conduct a long trip travel? Okay, definitely my charging plan will be affected. Okay, right? But within the survey, actually, it's very difficult to capture this type of impact. I'm gonna show you one example. Okay, based on our real world data. Secondary, they ignore the interaction between the electric vehicle charging behavior and the power plant operation. What does it mean? It means that they assume that the change of the EV charging schedule will not affect the operation plan of the power plant. This is not good, okay? But it works. For example, okay, in Illinois, in cities or states like Illinois, okay, where the market penetration of the electric vehicle is pretty small, for example, between 1 to 2%. Okay, we can assume that the change of such a small number of electric vehicles charging behavior will not affect the generation plan of the electricity. Fair enough. However, if we consider Shanghai, a city like Shanghai, there are over 1.8 million registered electric vehicles. Okay, so actually it accounts for it's already over 27% of the. This is not the sales market penetration. This is the total car ownership. Okay, it's close to 30%. So we cannot assume that hey, the change of their behavior will not affect the power generation plan, right? 30%. Okay. So we would like to develop a modeling framework to quantify the value of ordering the electric vehicle charging on carbon emission reduction by fulfilling the above two research gaps. Okay. Specifically, we are going to adopt the real-world electric vehicle user travel and charging behaviors, as well as the interaction between the electric vehicle charging behavior and the power plant operation. Okay, so that are the two research gaps we would like to fulfill. Okay, so regarding the data set we adopt, okay, actually we have the access to 10,000 electric vehicles, a small data set, I would say. But at that moment, it's already the largest data set at that moment. Okay, and about 60% of those vehicles are hybrid electric vehicles, and the remaining 40% are battery electric vehicles. Okay, in this study, actually we only consider the battery electric vehicles. Okay. And for each electric vehicle, we have the data, for example, their battery size, okay, and also the SOC, the state of charge, okay, of each individual battery electric vehicles. We also have the cumulative mileage. Furthermore, we have the location information, and we also have the state information. Okay, for example, whether the trip is whether the event is traveling, is charging or park. Okay, we have all this data. Okay, then with this data, what we are gonna do for each electric vehicle, we are gonna construct their travel time. The data lasts for we have the data over 11 months. Okay, so actually for each battery electric vehicles, we have such a travel chart for 11 months. Okay, so we can identify, hey, when the driver is gonna begin a driving section. Okay, when is the end of such a travel event. Okay, and when is the parking event. Okay, and of course, in addition to the time, we also have the location. Okay, and as well as the state of charge, okay, SOC of the battery at the beginning and at the end of each event. Okay, and now if we pay attention to T3 to T6, okay, this time period actually represents the time window when the electric vehicle is ready and available to recharge. Why? If you look at this window, you figure out that there is some charging event happen within this time window, T3 to T6. Okay, and the charging event happens at T4 and ends at T5. Okay, that means what? But from T3 to T4 and T5 to T6, I mean the vehicle are just parked there. Okay, it's not moving. Okay. So it means, hey, during this time period, the electric vehicle driver is ready to charge. Okay, they have the motivation to recharge their electric vehicles because according to the historical data. Okay, and furthermore, there must exist some available charger, okay, nearby. Otherwise, there will be no charging event. Right, happen during this time window. Okay, so we define such a window T3 to T6 as the charging time window. Okay, the charging window. Okay, the time from the last driving event before a charging section to the first driving event after the charging section. So that's the definition of the charging window. Okay. This is important, okay? So the time from the last driving event, you see, this is T3, okay? And the first the first driving event after the charging session, and that's T6. Okay, and then we can construct the time window. Okay, over 11 months for each individual the battery electric vehicles. Okay. The charging window is important. Why? Because during the charging window, the drivers will be ready and available to be charged. Okay, so what we are going to do, we are going to manipulate the charging plan within the charging window. Okay, only within the charging window. We are not going to consider the charging plan, for example, sometime between T1 and T2. Okay, because according to this data, we have no idea if there will be any charger available nearby, and also we have no idea whether the driver will have the motivation to recharge their vehicle. It's very likely that the price at that moment or at that particular location could be pretty high, so the driver will not have motivation to do that. Okay, so then if we define, okay, actually we divide the charging window into a series of time intervals. Okay, and the duration of each time interval, okay, we set it to be delta. For example, it could be 5 minutes or it could be 1 minute. Okay, and then we can divide the whole charging window into a series of intervals, right? And this this R means the R's time interval within the charging window. Okay, so CIJR is what? It represents the charging power for CEVs. Now CEV, it means the coordinated electric vehicles. I during the J's charging event in time interval R. Okay, so I would like to highlight one point. Here we define coordinated electric vehicles. Okay, think about that. Not all the electric vehicles, they're willing to work with you or to follow your order to change their charging schedule, right? So we just need to identify, or we just assume that, hey, there will be some electric vehicles, they are willing to follow my order. Okay, so we define these electric vehicles as the coordinated electric vehicles defined by denoted CEVs. Okay, so CIJR, if we sum them up like this one, we sum them up. Okay, with this is the power multiplied by the time interval, then this is the energy, right? The recharge energy. Okay, so this term is the total energy recharge during the J's charging window. Okay, so EIJ is what? Is the remaining energy in CEVI before the J's charging event. Okay, before the charging event, this is the remaining energy. Okay, and after the charging event, okay, then this number is the updated SOC. Okay, or the remaining energy of the CEV after charging, right? And QIJ is the electricity consumed by CEVI between the J's and the J plus 1 charging window. Okay, this is one. If you come back, we have all the data here. Okay, you can see. Okay, for example, after T7, there's going to be another charging window. Okay, and actually, according to the data, we can calculate, hey, the energy consumed between T6 to T7. Okay, so that's the QIJ. Okay, it's a parameter. Okay, that we can estimate from the historical data. Okay, so minus it, minus QIJ, okay, is equivalent to EIJ plus 1. It's just an energy conservation. Okay, so the decision is what? CIJR. Okay, if I don't want it to be, I don't want the vehicle to be charged, then CIJR is gonna be equivalent to 0. Okay, right? So there is a restriction. Okay, CIJR must be non-negative. In this paper, we don't consider the V2G. Okay, the vehicle to grid transfer. Okay, we only consider the regular charging. Okay, so the CIJR must be non-negative, and furthermore, it should not be greater than CIJ max. This is what you can understand it as the charging power of the charger. Okay, which can also be calibrated based on the historical data. And furthermore, after being recharged, okay, its remaining energy should not be greater than a threshold, EI max. Okay. So for this EI max, it could be just the battery capacity. Okay. But personally, for me, okay, I would choose to not, for example, the maximum SOC, I would prefer to set it to be 90% for the health of the battery. Okay. So, I mean, we can also calibrate this parameter based on the travel chain data. And also, okay, this is to guarantee that, hey, anytime the driver, the electric vehicle is not gonna running out of energy. Okay, it's gonna be no less than a threshold EI minimum. Such a threshold could be 0, but ideally it's gonna be 20% of the battery size. Okay, so we can also calibrate it from each individual electric vehicle's historical data. Okay, so given that, you can see what we're gonna do is we are gonna change CIJR. Okay, subject to these constraints. Okay, so this is the whole modeling framework. Okay, it's a bi-level problem. The upper level is gonna to determine the charging reschedule strategy for each coordinated electric vehicles from the perspective of strategy evaluator. Okay, its objective is what? Is to minimize the total carbon dioxide emission. Okay, by changing the charging plan. Okay, CIJR. Okay, for each CEVs. Okay, subject to that their travel chance will not be affected. Okay. So once the upper level manipulate those the charging schedules of for each CEVs, actually we are gonna change the aggregate electricity demand, right? And in the lower level, we are going to determine the electricity dispatch plan. Okay, the change of such electricity demand. Okay, how such a change will impact the electricity dispatch plan. Okay, we are going to make the decision from the electricity utility the corporation. Okay, in a way to minimize the total dispatch cost. Okay. So for the electricity utility, the corporation, they don't care about the carbon emission. Okay. What they need to care is the dispatch cost. They would like to maximize their profit, equivalent to minimizing the total dispatch cost. Okay, and then after solving the low level problem, it's going to determine the electricity supply. Okay, this is the electricity generation plan from a different plant. Okay, and at different time slot. Okay, and given that such a supply will affect the upper level's decision. Okay, because the electricity, the generation plan, or the dispatch plan will affect the carbon emission calculation. Okay, I'm gonna show you later. Okay, but if we look at the first, we look at the lower level problem. Okay, so this is what I mentioned. The electricity utility corporation aims to minimize the total power dispatch cost at each time interval t. Okay, such a time interval may not be the same as the one for the electric vehicles. Okay, what does it mean? It means if you still recall that for the electric vehicles, okay, the time intervals must be small. For example, every 1 minute or every 5 minutes. Okay, you cannot be 1 hour, right? You cannot say, hey, I'm gonna assume that within this 1 hour, you're not gonna be no charge, or you must be charged for the whole hour, right? Unreasonable. So such a time interval must be small. However, for the power plant, okay, such an interval should not be that small. Okay, at least it should be hour. Okay, so anyway, but for any time interval t, okay, the objective is to minimize the total dispatch cost. So here is a linear function, okay, MKT, and MKT is the on-grid tariff for plant K to generate 1 unit of electricity during period T, okay. So in the US, I was told that it's gonna be an auction based. It's kind of like a bidding process, but in China, no, it's not the case, okay, there's no bidding, okay. It's normally that the government, okay, is gonna set an on-grid tariff, okay, and you're gonna adopt such a tariff, okay. Good. And so GKT is the total amount of electricity generated by generator K at time t, okay. So the objective function is going to minimize the total dispatch cost. And the first constraint is what? Is to guarantee the generated electricity must be no less than the summation of the total electricity demand, including the non-electric vehicle demand, electricity demand. For example, it could be the industrial electricity demand, right? And some other residential electricity demand. And this LT is the, this term, okay? Is the electric vehicles electricity demand, okay? And divided by eta. Eta is just nothing, it's just energy transmission efficiency, it's just a parameter, okay? And the second and the third constraint is to guarantee that there is a maximum decreasing and increasing rate of generation for each plant. Okay, for example, within this hour, okay, for 2 sequential time window, you cannot change the generation plant so too significantly. Okay, so this is the constraint. And the fourth constraint is that the generated energy, electricity must be within, okay, the minimum generation capacity and the maximum generation capacity, okay. So these are all parameters, okay, and this is nothing but the input from the upper level, okay. How to generate, how the LT would be affected by the upper level decision. So, and then as what I mentioned, the lower level problem will affect the objective function of the upper level problem, okay? That's it, okay? The F function is to calculate the carbon dioxide emission, okay? For plant K to generate GKT electricity. Okay, so how to calculate this one? This is important. Okay, so actually, according to the literature, we we adopt, okay, not adopt actually, we calibrate such a function based on the real world data, okay? But in general, it's gonna be a polynomial function. Excuse me. So where the A, B, C, okay, are fitted the values for each plan K, okay? So we have no idea what's the value for A, B, C, okay? However, later we are going to calibrate those values based on the real world data. So anyway, given the lower level problems output, okay, this is the generation plan, okay, and then what we want to do, the upper level problem is to, hey, manipulate or optimize the value of C, okay, in a way to minimize the total carbon dioxide emission subject to these constraints, okay, where I have defined and introduced, okay. So actually, with these constraints, we can guarantee that the charging plan, the modify or the rescheduled charging plan will not affect the travel behavior or the travel trend of the battery electric vehicles based on the historical data, okay? And then overall, this is the bi-level. In the upper level, the objective function is to minimize the total emission, okay, subject to the constraint that rearranging the charging schedules while ensuring the travel needs of electric vehicles are met. And in the low level, so it's just simply a power dispatch plan to minimize the total dispatch cost while satisfying the electricity demand. Okay. So, however, such a bi-level problem is not easy to solve. Okay, if you think about that, first, it's a bi-level problem. Solving a bi-level problem is already complicated. Okay, even we can, for example, the low level is a linear problem. Okay, we can use the KKD condition to replace it and convert the whole problem as a single level problem. But with the complementary, the constraints is still not easy to solve. And furthermore, if we consider that for these constraints holds for each battery electric vehicles, okay, think about that. Nowadays in Shanghai, we have 1.8 million electric vehicles, okay. If we would like to calculate it for 1.8 million electric vehicles, you can think about the number of constraints, the number of variables, right? So it's a horrible number, okay? So, but anyway, the solution algorithm is not the focus of our study. So actually, we adopt the sensitivity analysis algorithm, okay, to solve this problem. The core idea is to approximate the upper level problem by determining the direction of change from small perturbations in the optimal solution of the lower level problem, okay? So we derive the KKD condition of the lower level problem, and we identify the sensitivity analysis, okay, of the action from the upper level on the lower levels output, okay? So we can modify it as this one, but we need to solve this problem iteratively, okay? So this is kind of like the approach. However, I would like to highlight that if you still recall that the constraints, the number of constraints and variables is highly affected by the number of electric vehicles that we consider in our problem. Once we convert it, if we adopt a sensitivity analysis method, actually, we can conduct parallel computing, okay? We're going to calculate, we can execute the solution algorithm for each individual battery electric vehicles parallelly, okay? By doing that, we can actually speed up significantly. No matter 1.8 million or 18 million electric vehicles, it will not affect our solutions efficiency too much, okay? And then Then we attend to the electric vehicle data that we adopt. So this study actually utilize the charging and driving data from about 4,000 battery electric vehicles in Shanghai, and over 11 months, okay, and includes more than 5 million driving records and 1.5 million charging records, okay. And this left-hand side figure shows the example of charging profiles of 3 vehicles, as we can see, okay, how the electricity, okay, will change as the time goes by. Okay. For example, if this is a stable, it means the vehicle will just park there. Okay, there's no driving. Okay, this is charging. If it's going up, this is charging, and if it's going down, this is driving. Okay, and this is the aggregate. The electricity demand for all battery electric vehicles, we aggregate them. Okay, to show you guys, you can see some patterns. Okay, and then in terms of the power plant data, actually we collect the local generator in Shanghai data. Okay, and because this data is public available, so we collect it easily. Okay, and also we can collect the share of energy source in Shanghai's local plants. Okay, for example, we have coal fire, we have gas fire, and we also have biomass and wind power, something like that. But as you can see the coal fire units. Okay, given the data, the proportion is close to 50%. Okay, it means that the electricity generation, okay, is not that clean, I would say, at least in Shanghai. Okay, based on this data. Okay, and also we list this is a list of the thermal power generators in Shanghai. Okay, and we also consider the external power supply. Okay, such as the Anhui East transmission project and several other projects to support the operation of Shanghai. Okay, and then we may use this is the data that we collect. Okay, and based on this data, actually we can calibrate the emission function, the carbon emission function, as like this curve. Okay, but if it looks linear. Okay, but if we enlarge it, we can see it's still a polynomial function. Okay, and also we can identify the minimum load and ramp rate of the generators. Okay, however, for the non-electric vehicle electricity demand, we don't have the data because the data is kind of like sensitive. It's not open to the public. Then we may use of the Shanghai's hourly load curves as well as the Shanghai daily peak electricity demand curves. Okay, based on these 2 figures, actually we generate the demand data by ourselves. Okay, such that new patterns can be realized. Okay, so some basic results. Okay, so as of July 2022, when we have the data, when we get access to the data, actually there were about only 380,000 BEVs in Shanghai. Okay, you can see within the past 3 years, okay, is a huge increment in terms of the electric vehicles, okay, in Shanghai. And at the moment, is the total number of battery electric vehicles roughly 100 times of the size of the data set. So we can consider our data set actually occupy 1% of the whole data set. Okay. So the charging demand for these vehicles is assumed to be 100 times of the data set that we adopt. Okay, because at that moment, we ask the officers from the center to randomly pick the battery electric vehicles. Okay, so we made such an assumption. Finding, okay, the carbon dioxide emission contributed by all battery electric vehicles is calculated to be this number. Okay, you have no idea. Okay, what does this number mean? But we convert it into gram, okay, per kilometer. So on average, the carbon dioxide emission rate for one battery electric vehicle is 73 grams per kilometer, representing 57% reduction compared to conventional gasoline vehicles. Okay, and this is the emission for conventional gasoline passenger cars. Okay, what does it mean? Okay, at the very beginning, some leadership of the national power grid in China, they have one concern. Okay, what if the electric vehicles charging behavior is not well regulated? Will the carbon emission brought by these electric vehicles be more than the one brought by the gasoline vehicles? So this is the answer. Okay, without any optimization, without any reschedule, okay, electric vehicles can still reduce the carbon dioxide emission significantly. Okay, and this is the charging schedule before and after optimization. Okay, for a 1 week period. Okay, for one vehicle. Okay, I just use one of the vehicles to demonstrate. Okay, this color bar means the charging window. Okay, as we can see, no matter before and after the optimization, all the charging event will happen only within the charging window. Okay, and we can see a huge difference before and after the optimization. Okay. The blue one is the original schedule, and the red curve represents the optimized one. Okay. And this is the SOC transition before and after the optimization. We can also see a significant difference. Okay, and this is the cumulative one. Okay, and this is the charging demand variation over time for all the coordinated electric vehicles. Okay. We can see a significant change. Okay, from the blue curve to the red curve. Okay, this is the aggregate one. Okay, and this is the seasonal changes in emission reduction. We can see in the summer, actually the emission is the highest, and as a result, the reduction per coordinated electric vehicle per day is also ranked the highest. Okay, but in terms of the ratio, okay, actually the often, okay, in often, the ratio, the reduction ratio is the maximum. Okay. And we highlight that not all the electric vehicle drivers or owners, they are willing to be to kind of like to participate in this game, to follow the order of the central government or the strategy evaluator, right? So we test such a proportion. Okay, for example, 0.01, it means that only 1% of the battery electric vehicle drivers, they are willing to cooperate with the central government. Okay, then what's going to happen? Okay, as we can see, as we increase the proportion of the CEVs, okay, the reduction ratio will keep increasing. The more electric vehicle that we can control, definitely the more carbon emission that can be reduced. Okay, fair enough, right? However, if you consider these bars, this is the CO2 reduction per CEV per day. Okay, we can see the reduction is become marginal. Okay, it means what? It means that there's no need to control if we only have a certain budget available. Okay, think about that. If you would like to ask some driver to listen to your order, then definitely you need to pay some or design some incentivized scheme. okay, to encourage them to modify their behavior, right? There is a cost, okay, and this is the benefit, okay. You figure out that the cost and the benefit, we need to balance it, okay, in reality. It's not the more the better in terms of the reduction, okay. So it just shows you a decrease in the marginal impact, okay. And what if we consider the battery size? For example, we can. What if the battery technology is advanced? Okay, the battery, the electric vehicle has a larger battery. Then what's the impact? Okay, so it shows, this figure shows that additional battery capacity can actually increase the reduction ratio. Okay, however, such a reduction will also kind of like become the increment of such a reduction will become marginal. Okay, as the battery becomes larger and larger. And this is the impact of planned ramp rate on emission reduction. Okay, it means if the ramp rate is larger, it means what? It means the power plant is more flexible in terms of the electricity generation. Okay, if it's more flexible, it means it suggests that, hey, the impact, the benefit brought by the CEV, okay, is actually will be kind of like reducing. Okay, fair enough. Okay, because now the power plant becomes more smart. Okay, then the reduction, the contributed by the CEV side is going to be less. Okay, and also we consider that, hey, what if we introduce additional wind power capacity, okay, to the generator, to the power plant, okay, and then what's the impact? Okay, so as we can see, if we add more the wind capacity, it means the source to generate the electricity becomes more clean. It's cleaner. Okay, then as we can see, okay, the value, the CO2 emission reduction is actually decreasing. Okay, because the energy is cleaner, then definitely the carbon dioxide emission will be reduced. Okay, the contribution from the CEV. Okay, however, okay, the reduction ratio is keep increasing. It means what? It means, as we have more clean energy, okay, the original emission, the original carbon emission contributed by the BEV is also decreasing significantly. Okay, it's even faster than these parts. Okay, and as a result, it's increasing. Okay. Okay, it's over, right?
Yeah.
2 minutes, right?
We're not gonna leave it right now.
Oh, okay, sorry. Okay. Okay, I'm gonna skip it. Okay. So here's the conclusion. Okay. Yeah.
Thank you so much, Professor, for the amazing presentation. Can you take questions? Not
Thank you for the great presentation. I had a question about the charging window.
Okay.
Because you mentioned it's very important. And right now you're considering it to be like from the driving cycle before the charging until the next driving one.
Right? This one.
Yes. So I was wondering, like, if the vehicle is being parked but not being charged the whole time, it's during like the parking of the vehicle.
Yes, it could be.
But would that be considered in this driving, in the charging window?
Yes. Yeah.
But the charging window also includes the parking.
Oh, you mean this part?
Yeah, because it's It's from T3 to T6, right? The
Yeah.
charging. So
Yeah.
it includes also the parking, not just the charging, right?
Yes, but if you look at this one, you figure out that between T3 to T6, actually the car is not moving. Okay,
Yes.
so it means what? It means that it can be recharged. It can be recharged anytime between this time window.
Yes.
So, yeah,
My question is like, it could be not all of T3 to T6 is charging.
of course, yes. We just need to set, for example, at T3, you don't want it to be recharged, right? You
Yes.
just need to set the corresponding CIJR to be 0.
Oh,
And then that's
okay,
not
okay,
charged.
okay, thank you.
Thank you very much for your interesting presentation, Dr. Chen. I wonder, building on the previous question, maybe there is a reason because the vehicle is parked and not charging? Maybe there is congestion at the charger level, or maybe there
Yes.
is a pricing signal that motivates the decision.
Yes.
So could there be like such impacts? Essentially inherently suggests that you need more ports facilitate this type of management.
Yes. Yes.
Or some other.
Yes. I mean, it's great question. Okay. Actually, we try to solve it. There is another center, okay, in Shanghai, only collect the data from the charger. Okay, and this center only collect the data from the vehicle. We reach out to the other center to request for the data. I mean, if we have both the data from the station side and also from the vehicle side, then it's going to be a complete data set, right? But unfortunately, they are not willing to provide me the access. So, yeah, we cannot do anything. I mean, yeah, but you're right. Okay, this is a strong assumption, I admit. Okay.
Thank you very much.
Okay,
No, it's, oh, okay. Okay, and thank you also for the very interesting presentation. I just have a quick question about the your sort of choice of the upper and lower level. I've been wondering who is the leader, who is the follower here,
Okay.
and why. And also another related question is that the different you use individual EV as the leader here, right? So you have multiple leaders. And then, is there any way you can aggregate them? Since the spatial dimension is not really an issue here, right? You have some Shanghai traveler, you are focusing on the temporal dimension, the windows. Is it possible to aggregate the EVs into sort of flow instead of having individual vehicle? If you look at essentially use a continuous variable even to say what's the number of, you can treat it as continuous to avoid this integrality.
Oh,
I don't know if I'm clear in that question.
Yeah. I think I get your point. So first, in terms of the decision maker, right?
Mhm.
The upper level is going to be the strategy evaluator. Okay, think about it from the government's perspective. Okay, what I want to do is to investigate the potential. Okay.
Well, or the other way is that you may have infeasibility in the lower level. If you for certain upper level, maybe your lower level, your power generator cannot. You have a generation lower
Yeah.
bound there. You may not be feasible.
Yes, you're right. So when we solve the problem, actually we need to consider that as well.
Yeah, I was just wondering who
And-
makes a lead decision.
And in terms of your second question, okay, I mean, if we can aggregate them,
Mm.
that would be perfect. It means that we don't need to treat each vehicle individually.
It's just a sort. Yeah.
Yeah, I mean, we also think about that, but we don't have a solution to that. Okay, but now the problem involves no integer variables.
Mhm. Yeah,
In
that's true.
this case. Yeah. However, if we can consider the vehicles as continuous, I mean, then we can use the traffic flow theory, right?
Yes, yes,
To
that's what
treat
it
it, then that would be great.
Yes.
Yeah.
Thank you. No,
Thank you.
I'm sorry, we're out of time, so if you have any questions, like Professor is gonna be here, you can ask him. Everyone, let's thank Professor Zhibin.
see some questions online, right?
I see where giving some suggestions.
Oh.
But we corrected that. When we got the latest. And then I got the. That's way, that's way.
That's what I was gonna say. But my question, you understand my question? Who is the leader? Maybe in China, it's I don't know who is the leader. I'm from China, but I don't know what's the political system.